we'll now talk about a more formal definition of what the derivative is in calculus. So we've got y as a function of x, and if I was to draw just a curve, we know straight lines are easy to find rate of change, but if we want to find the rate of change, instantaneous rate of change with a curve, it's quite a bit more involved. So here we've got our x and our y. So any function we've got there, y is a function of x. And if I make point P here, and if that's an x value, then when I substitute that x value into the function, I get f of x. So P will be the point x, f of x. All right, so if I went across over to here, that will be f of x. And I have another point here, q. Now q is quite close to P. So the way to write that is that we'll say that we just increment or increase this x value by a small amount of x, and we'll call that delta x. Okay, delta x means in this case a very small increment of x. Now I've drawn it, it doesn't look like delta x is smaller than x even, but just to be able to see what's going on here, I've made delta x quite large, but there'll be reasons for that as we progress. So what I'm indicating here is that delta x is just a small increment of x. So q would have the coordinate of the x value would be just x plus delta x. Now when we substitute the x value into the function, we get the y value. So it will be f of x plus delta x will be the y value. Okay, so there are my two values. Now we saw in the previous video that if we want to get the instantaneous rate of change of f of x as x increases, as one quantity increases with respect to another, if we want to know exactly the rate of change at this point where we've got x is equal to x, we would need to be able to calculate, maybe if I do it in a colour it might stand out a bit more, we would need to be able to calculate the gradient of that blue tangent at point P. So that will give us rise over run, the rate of change of f of x as x increases. So we can just do rise over run, so that's my rise, and that's my run, and that would be the gradient of the tangent, and that would give me the instantaneous rate of change of this function as x increases at that point P. Okay, so how can we do that? And that's what calculus and that's what the derivative allows us to do. What we've got to think about is this, is that what we're going to do is incorporate our knowledge of limits. And if we've got point Q, if we move point Q, and once again I'll get another colour here, if we move point Q to there, and then we calculate the gradient of that tangent, of that straight line. Now, when you connect two points on a curve, that straight line is called a secant. So secant, this green secant here, the gradient of that is going to be fairly close to the gradient of the tangent, which is the blue line here. All right, we move Q a little bit closer still to there. Well, the gradient of that secant from P to Q is closer and closer still to the gradient of the tangent. So we'll use our knowledge of limits and we'll say, okay, it's going to be the gradient when delta x, this small amount of x approaches 0. And so our formal definition goes a bit like this. So this is the formal definition of the derivative. Now there are a number of ways of writing the derivative, but dy dx is one way, or f dash of x is another way, or y dash is another one, sorry, y dot is another one. So they are all different ways. Now we can go dx of y. That all means the same thing. That means the derivative of y with respect to x, the instantaneous rate of change of y as x increases. That's what we're calculating. So a little bit of syntax there for how to write it. So dy dx equals, this is my definition, the limit as delta x approaches 0. Now what happens there? As delta x approaches 0, it means q gets closer and closer, and so close to point P that it's almost there. It's as close as you can get. So the limit as delta x approaches 0. What is the rise? The rise is that difference from y minus that one. So it'll be f of x plus delta x minus f of x all over. So that's the change in y. Here's my y1, or my 2 minus y1 over x2 minus x1. So x2 minus x1, so that's x plus delta x minus x. So when I simplify that, I get to that. So this is a formal definition that you need to commit to memory. The derivative, the formal definition of the derivative. It's the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. And it's nothing more than the instantaneous rate of change of the function as x increases. In other words, it's the gradient of the tangent at a particular point. Now, we have said that P is any point, so this will give us the instantaneous rate of change at any point along the curve. Doesn't matter whether the curve's going like that, or I can extend the curve further and make it go up and come down. This definition here will allow us to calculate the exact value of the gradient there, the exact value of the gradient there, by just substituting in the different x values. So I'm going to come back and do some formal practical applications, and then I'll do some shortcut applications and ways to get to the derivative very, very quickly.